Today, we're going to be discussing an awesome and interesting subject. This subject is near and dear to a little acorn's heart. What did the little acorn say when he grew up? Gee, I'm a tree! Menelaus of Alexandria's story is contained in one of his books and in other astronomers' writings such as Ptolemy. Spherica was written in 3 books, but only one of them survives. In that one volume, the spherical triangle was introduced. This is mentioned in Ptolemy's and other Greek astronomers' writing. Not too much is known about this man, other than he was a Greek astronomer and mathematician that was believed to have lived in Rome between 70 and 140 CE. As you've been working through your geometry class, it's time to take some of the basic concepts that you've learned and mesh them into one proof that has many different versions, but we can do this one with just basic knowledge of geometry. Menelaus' theorem states that given any line that transverses or crosses the 3 sides of a triangle, the product of 3 non-adjacent segments is going to be equal to the product of the other 3. This essentially means that if you have triangle ABC with x, y, and z on sides BC, AC, and AB respectively, and given that x, y, and z are collinear, then you're going to have the ratio of AZ over BZ times BX over CX times CY over AY is going to be equal to 1.
Before we begin the actual proof, there's some things we have to go over. For this proof specifically, we're going to need to go over the idea of similarity. Similarity says that 2 geometric figures are similar if they have the same shape but are of different sizes. Some of the criteria includes angle-angle, side-side-side, and then side-angle-side. Side-side-side criteria states that triangles are similar if the ratio of the side lengths is proportional for each set of corresponding sides. Once again, we can prove this easily using angle-angle criteria. If we lay the 2 triangles on top of each other, base sides are parallel, base angles are equal to each other, angle-angle criteria is sufficient, so both of these triangles are similar. In this proof, we also use the idea of vertical angles. Basically, all it is if 2 lines intersect one another, the opposite angles are going to be equal.
In this section, we're going to look at how to create the side ratios of the corresponding sides of 2 similar triangles. So let's pretend that we've taken triangle 1 and triangle 2 to be similar by angle-angle criteria. Just as a recap, we can pretend that angle B corresponds to angle X in triangle 2, and angle A in triangle 1 corresponds to angle Z in triangle 2. That means that angle C and angle Y in triangles 1 and 2 respectively had no other choice but to be equal. So let's look at side AB in triangle 1 first. We're going to set up our ratio, and all of the side lengths from triangle 1 are going to be in the numerator, and all the side lengths from triangle 2 are going to be in the denominator. So AB is lying across from that green angle C. If you look at triangle 2, the angle that corresponds to angle C from triangle 1 is angle Y, and angle Y sits across from side XZ. Okay, let's work with side AC in triangle 1. That is across from the blue angle B in triangle 1. In triangle 2, the blue angle X is corresponding to B, and it's across from side YZ. Lastly, we have the red angle. So up here on the numerator, we're going to have BC because BC is sitting across from the red angle A. In triangle 1, angle A corresponds to angle Z in triangle 2. Angle Z in triangle 2 is sitting across from XY. So here we have the side ratios for 2 generally similar triangles. Now, we're going to see if we can apply these to the triangles that we have proven to be similar in our specific proof.
Now we're going to get into the proof of Menelaus' theorem. So to set up Menelaus' theorem, we have a line going through a triangle such that it hits all 3 sides and it does not go through any of the vertices. And there are actually 2 cases here, and the first case is what I've drawn. So the line intersects two sides, actually on the sides within the triangle, so it's on the actual sides. And the third intersection, you'll have to extend out the third side. So you can see here I've extended out AC, and it intersects right there. And the other case would be you could have a line totally outside the triangle, in which case you would have to extend every side. But in that case, it's a lot harder to draw. The picture would be a lot bigger, so I'm going to stick with this case, but the proof is exactly the same. So the next step is to, well, I'll label these points. This point is F, this point is G, and this point is H. Now, what's the theorem? The theorem says if I take the ratio AH over BH, so AH over BH, and this is just the ratio that the line here divides side AB into, and multiply this by the ratio for side BC, so that'd be BG over GC. And for the third one, which is the side that we had to extend out, it's the same thing. So we're going to have CF, so CF over. Now the third one is this be this long side here. Oop, that's not what I wanted to do. So it'll be this ratio, CF over FA. FA. So now if you take the product of these three ratios, which is what the three ratios that the line divides each side into, this will give you 1. Now, in order to prove Menelaus' theorem, well, first of all, I'm going to erase this statement. I'm going to erase the statement of the theorem, and then I'm going to draw some perpendicular lines from each vertex. Now, this is called dropping a perpendicular. So that's the first step. All right, now I put in these 3 perpendicular lines here. Okay, and I'm going to label the points where these perpendicular lines hit the big line going through the triangle. So this point corresponding to A, because A is the first vertex, this point will be point Q. That's point Q. This point here corresponding to B will be Q point R. The point corresponding to S will be, or point corresponding to C will be S. Now, because these are perpendicular, that means this is 90 degrees, this is 90 degrees, and this is 90 degrees. All right, now I'm going to erase these little 90-degree symbols because they're sort of cluttered up the diagram. So just remember that those angles are 90 degrees. So now the basic structure for the proof is using similarity of triangles. We're going to prove several sets of triangles are similar. The first one is going to be triangle BRH, which is right here. This BRH. All right, and then the other one will be AQH, so this one right here. All right, so I'll just go ahead and write those down. So that is a bad triangle symbol. So triangle BRH and triangle AQH. Okay, now let's see what we can find in common. We can see these two angles, which will be angle BHR and angle AHQ. AHQ. You can see those are vertical angles because it's formed by two intersecting lines. So those are vertical angles. So those are equal because vertical angles. All right, then we can also, if I get rid of those, notice that because BR and AQ are perpendicular lines, then this angle here, which is BRH, and this angle here, angle AQH, those are both 90 degrees because they're perpendicular, so it means they're equal because they're both right angles. So right angles. Okay. So now we have two angles in common. So that means we have if two angles in each are equal, that means they're similar, because AA similarity criterion. So those are similar. So now I'm going to keep track of this by putting it up here. Oops. All right, so let's keep track of the similar triangles we have. So we know that triangle BRH is similar to triangle AQH. Okay, so that's the first set of triangles that are similar within this diagram. And if I just erase all this, the next set of triangles that are similar will be oh, that's it. I was trying to erase triangle CSG, which is this little one in here. So CSG, so it's a little triangle. This will be, this is the first triangle to consider. The second triangle will be triangle BRG, which is this sort of big triangle. So BR all the way down to G. So sort of along here is the triangle. Now, can I do that? All right. BRG. Okay. Now, let's see what we have in common here. So, this angle here, which is angle CGS, so angle CGS, we can see that that's, and this angle here, which is angle BGR, those are vertical angles made by two intersecting lines, so those will be equal. And I'll put vertical angles in my bad handwriting. I apologize for that. So the other two angles we have, well, if we remember that this angle BR, BRG in this triangle, this angle here is a right angle because that's a because BR is perpendicular, and then this angle here, which is CSG, that's also 90 degrees because CS is a perpendicular. So then I can say, and it's going to delete my writing if I write below this line here. Yeah. So why did it just do that? What is this? It is a CSG and angle. That's angle BGR. Oh, it deleted that too. That's what you get for using technology. So angle BRG or angle BGR will be angle CGS. Okay, so now let's not do that again. So I'll make this look better. This will be these two 90-degree angles here. So angle BRG will be equal to angle CSG because they are right angles. Okay. And is that all? All right. So, well, once again, we have two angles that are equal in both triangles. So by angle, we have they're similar. Now, like before, I'm going to keep track of it up here. Triangle CSG is similar to triangle BRG. Okay. And if I go down here, the last set of similar triangles, it's going to be slightly different situation than before, but it'll all be good. We've already learned the different kinds of similarity, which I think it'll still be angle. So the last set of triangles will be triangle AQF and triangle CSF. Now, these are, if I get rid of these little angle markers. All right. This triangle CSF, CSF. So this triangle here, and the other triangle will be AQF, which actually sort of will contain CSF. So AQF. So you have triangle AQF and triangle CSF. If you see it, so all right. So CSF is sort of inside AQF in the diagram. Okay, so the first angle, I'm actually going to do the right angle first because it's the easiest one to see. So we can see these angles, angle AQF and angle AQF and angle CSF. CSF. Those are equal because they're both right angles. Right angles. All right. Now the other angle that they have in common isn't a vertical angle like before, but it's actually this angle right here. As you can see, this angle is in both triangles. So AFQ and angle CFS are actually the same angle. So, and what angle was that? Angle AFQ be equal to angle CFS because it's the same angle right here. So I'll write same angle. Alright, so that's the third set of triangles that are similar. Now, I'll go ahead and put it up here in our little notepad. So that'll be triangle AQF. Will be, oh, and these are similar. Similar to triangle CSF. Okay, now we've got all the machinery done. Now the left is just to, all that's left is to put it together. So the first thing, now that I'm going to do, I was going to give a couple names to some lengths. So this length here, I'm going to call T. So length of AQ, so I'm going to write length of AQ is T. The length of, my handwriting is very bad. Length of BR is U. And length of CS is V. Now, unfortunately, in mathematics, we use U and V a lot, and U and V look very similar. So I'm going to try to keep these looking, U and V looking as different as possible. Okay. Now I'll write these in the diagram. So this is already T. This is already T. And why does it always move? So T. Then this will be U. And this will be V. Not a U. Okay. Now, if you recall, if you have similar triangles, the ratios will be the same. So, what I'm going to do is I want to note that with these triangles, BRH and AQH, BRH and BRH, that's still trying to erase, BRH and AQH, that, what will that be? So, AH over the corresponding side in the other triangle, which is HB. And these are similar. These two triangles are similar, so the ratio of this side to this side will be the same as the ratio T over U. Now, in the next set of triangles, I'll just leave it right here. So in the next set of triangles, CSG, which will be this triangle, and BRG is this big one here, we can see that the ratio of this side, which is BG, to its corresponding side GC, so BG over GC, and that will be equal to these two sides correspond, so that'd be U over V, and finally, if I get rid of these extra things here, oh, and get rid of that. And finally, for this last set of triangles are right here, AQF and CSF. These will be, if I can see that, CF, F over, what is it, FA. So CF is in triangle CSF, and FA is in triangle AQF, then this ratio here will be equal to CF over FA will be equal to the ratio V, because this side corresponds to the side, so V over T. Now, I have written these ratios, I've written the names of the sides very carefully. I've chosen that carefully. You do that a lot in math. You do things in such a way so that it makes life easier for you. So I've chosen these such ways. So those are the three, each one of these are the three ratios from the statement of the theorem. So this, if you recall, statement of the theorem had to do with the product of these three ratios. So AH over HB times BG over GC times CF over FA. All right, this is what the theorem was all about. This product, and it's gonna erase a bunch. Oh, awesome. So, well, we have values for each of these now. So, if I'm gonna rewrite these three ratios up here smaller so they're not in our way. So, AH over HB is T over U. BG over GC is U over V. CF over FA is V over T. All right, now, if I erase these, now, all right. So now, what's the product of these three ratios? Well, that's just going to be AH over HB. Up here is T over U. Then, let me erase it. All right, and then BG over GC is right here, is times U over V, U over V. And finally, right here, CF over FA, which is the same as over here, this will be V over T. Okay, now, what does this equal? Well, you can see there's a T being divided by a T, a U being divided by a U, and a V being divided by a V. Now, because we set it up such that none of these triangles here, or none of these, or this line here does not go through any of the vertices. None of these will be 0. So that means you're not going to have any zeros divided by 0. So T over U times U over V times V over T. The T over T will be a 1. U over U is 1. V over E is 1. So the product of all threes is just 1, which that's the theorem. Now, that's at the end of a theorem. Always, well, once you prove the theorem in math, nowadays they'll just write a little square, right? A filled in square, but that square still represents an old Latin phrase QED. I still like writing QED. So we've proven the theorem. And after this, actually we're going to do the converse of the theorem, which goes the opposite. So if the theorem is saying, if you have this line going through if you have this line here going through a triangle, and the product of these three ratios is 1, the converse is going to say the opposite. Now, I'm not going to do the converse, so we're going to switch again. So, but this theorem itself, this direction of the theorem, has been proven, and therefore is worthy of a QED.
Now that we have gone over the proof, we will quickly go over the converse. The converse states that given triangle ABC with L, M, and N on sides AC, BC, and AB respectively, we get that AN over NB times BM over MC times CL over LA is equal to 1, then L, M, and N are all collinear. We have already drawn our picture, and we have drawn it just so L, M, and N do not look collinear at first. To go ahead and prove that they in fact are, I will go ahead and draw a new point that is collinear to L and M, and I will call that N prime. From the theorem, we now get that AN prime over N prime B times BM over MC times CL over LA is equal to 1. Since both of our equations are equal to 1, we get that AN prime over N prime B times BM over MC times CL over LA is equal to our original equation, AN over NB times BM over MC times CL over LA. Through the use of algebra, we can go ahead and cancel out like terms here, giving us that AN prime over N prime B is equal to AN over NB, thus ultimately giving us that N prime is equal to N, meaning that N prime and N are the exact same point, thus giving us that N, M, and L are collinear.